There's homework due today. The homework was to create a little function that we can call from C to compute the Hamming value of this number, Hamming weight. And this is the function you're creating. It takes a single argument that is an unsigned 32-bit integer, and it returns a single return value that's an unsigned 32-bit integer. And whenever you see a function prototype like this, you can imagine it having an extern in front of it. In fact, if we put an extern in front of this, the compiler will accept it just fine. There you go. And so it sees this and knows that somewhere someone is going to provide a function named Hamming that is callable using its standard calling interface, the AMD64 stuff, and will provide values and returns in the appropriate way. And here is the little template I gave you. Up here we do some stack stuff. Down here we do some stack stuff. We need to do all of this because, again, we're being called by this main program. So there's a caller that has its own base pointer and its own stack pointer and its own registers doing stuff. And we're expected to be a good citizen and abide by all those rules. And so if we modify this stuff, we're expected to put it back. The important thing to remember here is that leave is the same as these two instructions. So leave modifies both the stack pointer and the base pointer. Keep that in your mind. It's just the same as these two. And again, I'll be switching back and forth so you keep seeing these different ways of doing it because you'll see both in practice. In here, well, where's my argument? Where's my return value? The calling convention tells you where to find those. Let's talk about tools, and in particular about the data display debugger. I'm not going to go through all the details of it here. I made a little video and uploaded the video which walks through using the data display debugger. I did this actually last year, so things evolve, and some things may look a little different in the modern one than in the video, but the basic principle is the same. It's got maybe a little bit of a dated interface, but it's nice in that you can present a lot of information and it's maybe in a little more friendly way than if you're doing it from the console, although I find myself most commonly using GDB from the console. And so there's a little video that discusses that. It's up on iLearn for this class. Let's go back and continue our discussion from last time of dynamic linking. And so as we get into this, let's think about the three stages of building a program. There's assembly or compilation. That's where I take whatever the input language is, like NASM's language or C or something else, and I create the bytes that make up the assembly instructions. Right? So for a language like C, I'll take the C code, turn it into an intermediate representation like register transfer logic, turn that into assembly, and then assemble it. For an assembler, I just skip all those initial steps. I write the assembly directly, and then I turn that into the bytes. So remember, the assembler organizes my code in sections. And it knows what code goes in each section. And because it's converting, for example, add with carry, it's converting that to the actual bytes, it knows how many bytes there are between instructions in each section. Now, there's a little bit of a caveat there. So, suppose that I have a jump or a branch within a section. And I want to choose the smallest instruction in every case to accomplish that work. So if I can use a single byte to hold a signed 8-bit offset to get to the place that I'm branching or jumping, I'll do that. On the other hand, if I can't do that, maybe I'll move to a 2-byte or maybe even a 4-byte offset. Doing that, of course, changes the number of bytes, which might change the offset I need for another instruction. So a lot of times assemblers will have a couple passes where they go through and try to initially figure things out and then go through and verify that they figured it out correctly. And some of that happens. But at the end of the day, the assembler knows this is how many bytes everything takes. And so the distance from point A to point B inside a single section is known, and it can fill in that information. So if I reference something like a data byte, or I reference another routine or a label within the same section, the assembler may be able to resolve that for me, and it probably will. When I reference something outside of a section, like I reference a data object in another section, the data section, the assembler doesn't know what that is, right? The data section probably has different access controls than the text section. Right? The text section is executable and read-only. The data section might be read-only, but it's not going to be executable, and it might even be that it's writable or not writable. And so it doesn't know where that's going to be in relation to the program. And so it creates a relocation record that says, hey, I've got a problem. I don't know where this is, but I'm going to tell you I need you to find an address or an offset or something else and put it at this location once you've figured it out. And it hands that work off to the next stage. The next stage is the linker. So once I've assembled all the different component files, so I may have dozens of .o files lying around, and now I need to link them. And that's true whether I've done C or Rust or whatever. I need to solve the program linkage problem. And so the linker opens our little .o files up and looks for static relocations that it can solve. And we'll think of these as link time relocations. The linker knows more than the assembler did. The linker's job is to then lay out how the different sections relate to each other and organize them into these memory segments that have their own protection scheme. And so the linker will know how far a data object like a text string is from the instruction that wants to reference it. And it can fill that in. It can use an offset to fill that in. And if it uses an offset, that's great. Because again, the offset just says, go get the bytes that are 1016 bytes further along and load them here. And I don't need to know any addresses to do that. I just need to know that, oh, it's this much further. That's the magic of the RIP relative addressing. I can move my program around anywhere I want to put it in memory, but those offsets don't change. And if I write my program using just offsets, I'm good. So it can fill a lot of these in, but occasionally there are things that the linker needs to know that it just doesn't know. The most obvious case is it doesn't know the addresses of routines from dynamic libraries. So when we compile a program statically, we load all of that library stuff into the ELF file. So it's all together in the ELF file. Remember, the linker knows how things are laid out in the ELF file, so it knows those offsets. So when you statically link a program, you don't have any stuff to worry about dynamically later. But we don't want to do that. We want to save some space in our ELF file. We don't want to put all these libraries in there. We want to use the ones that are already loaded onto the system. It'll be faster, more memory efficient, lots of good things. And in addition, they'll be randomized, and that's a security feature. So the linker doesn't know where these are going to end up, and it won't know until runtime. And when we talk about runtime, we mean dynamic. And so the linker leaves some relocations, or it may leave some relocations in and says, I don't know how to solve these. I need real addresses. I need real virtual memory addresses, real VMAs, and I don't know what those are. So I'm going to leave this problem as a relocation for the loader. I'm going to say, loader, when you know an address for this symbol, replace these bytes with that address. And that's a dynamic relocation. So then we come to the loader. So we've seen the loader. If you look at the program using objdump, you'll see an interpreter is specified. Or you just run file on the program for dynamic, you'll see an interpreter specified for the dynamic executable. The interpreter is the dynamic loader or the dynamic linker. Any of those are all synonyms for the same thing. Some people just call it LDSO. That's fine. That's the program whose job it is to solve the dynamic relocations. Those last few relocations that are left over that the assembler couldn't figure out, the linker couldn't figure out, that usually require absolute virtual memory addresses to be specified. The loader has initial information. It knows where the program has actually been loaded into memory. And it uses that information, along with information about where the system has loaded the dynamic libraries, where they're mapped in memory, to solve that problem for us and patch those last few relocations, those dynamic relocations. And then, once that work is done, the program can run. And there's two different ways it can do it, and if you want to know more, there is a video about relocation read-only that is in iLearn for this class. If you watch that, actually walk through in GDB how those two different schemes work. But basically, the dynamic loader solves that problem for us. Assembly, linking, and loading. The global offset table. We're going to resume our discussion of that. And I point out again, this is worth knowing about because it's still there. It's still something that can be a security vulnerability in your code. There are some protection schemes for it, but it's still there. It's worth knowing how things work under the hood. You probably won't have to work directly with it unless you're on a different platform, or you're working with 32-bit code, or you're writing malicious code, or you just want to know how this stuff works. So I think it's worth knowing about. And we'll do a little review from what we covered last time. So I'll go pretty quickly through these first few slides. Remember, our basic problem was we have relocations that occur in the text section, or in the text section. And patching those at runtime means modifying the text section at runtime for the program. And for a variety of reasons, we tend to think of that as dangerous. We mark the text section as read-only for a reason. We don't want it to be modified. We'd like it to be static. Well, how do we have dynamic relocations then? Because we know we need them. How do we have them? Well, we move all those dynamic relocations into a table, the lookup table, called the GOT. And in our code now, where we would have had a dynamic relocation previously, instead we have a reference to the GOT. And inside the GOT, then, is where the dynamic relocation occurs. How do we reach the GOT? Well, again, the linker knows the distance between things that are part of the ELF file. And the GOT is going to be inside the ELF file. So, I mean, it won't be filled in. It'll just have a whole bunch of spots for relocations. But it'll be there. So the linker will know how far from an instruction that needs the GOT to the GOT we are. It'll know that distance, and we can use RIP relative addressing to get to that, and then we can use the dynamic relocations to fill in the GOT and solve that whole problem. So the GOT is this well-known table that we're going to be using. There's a global symbol called global offset table. It shows up in the symbol table. You can look at the symbol table for a program you write, and you'll see global offset table in there because it's still in there in the 64-bit world. It's just less obvious to us for various reasons that we'll talk about now. How do I use it? Well, suppose I knew where it was. Suppose I actually had the VMA of the global offset table. Then I could get things relative to it. if I then knew the offset from the global offset table to the thing I wanted, I could use that to get it. I would just add the address of the global offset table to the offset, and I'd be in good shape. And I can do that at runtime. One way to do that is to use this little piece of NASM syntax. This is NASM stuff. If you do this in the GNU assembler or in MASM or elsewhere, it'll be a little different. But this says, I want to reference a thing. It might be memory, it might be a routine, it might be any old thing, with respect to the GOT. And so give me back the GOT offset to that thing. So when this occurs in the program, it instructs the assembler to create a link time relocation for the signed 32-bit difference thing minus global offset table. So what does that look like? Here's the start of thing, and then down here at lower memory is the GOT. And so this is going to have some high address, this has some low address. I take the difference, and that gives me the distance between them. Okay. So now, if I know the address of the global offset table where it starts, I can add that difference to it and get the absolute virtual memory address of thing. And that's how we do it down here. Pretty straightforward. That's the simplest use of the GOT and the WRT for dealing with it. Very straightforward. But notice, this gets us the address of a thing that that maybe is in our text section, or maybe it's in the data section. It's somewhere in our program. So let's try that. So here I take the global offset table and I move it into RBX. And traditionally, EBX or RBX, depending on 32 bits or 64 bits, is the register that held the address of the global offset table, and then you would use everything else relative to it. Now, RBX is a Kali saved register, so if you're going to use it, you need to push it and restore it, etc. I'm not going to worry about that here because we're just not going to worry about that right now. So now that I've got the address of the global offset table, I can add this offset. So I want to get the message. And so I can say message with respect to the GOT offset and get the address of message. Simple stuff. But when I go to build that, it tells me I can't do that. It says GOT off references must be QWORD. They must be an actual 64-bit offset. And this is not. I've already told you this is a signed 32-bit offset. And go back to this. Suppose that the GOT is laid out here after the text section at higher memory. That's still okay because taking the address of a thing and subtracting the address at the start of GOT at higher memory gives me back a negative offset, and that's fine. So this doesn't work because this is 32 bits. RBX is 64 bits. That's not going to work. So the solution is to move this 32-bit offset thing out of those square brackets. And this will work. So what happens here is for this move instruction, the assembler creates a link time relocation for this value. And the linker then patches it with the actual constant offset. So this may look like I'm trying to take a 32-bit thing and shove it into a 64-bit register, but it's really, like I said, move RDI minus 17. And it's going to, it's going to do the 0 extension or the sign extension to make that work. So this will work just fine. So this will get us access to stuff like this message down here. It's probably overkill for that because, again, we have RIP relative addressing, and we could really get message using that, and we'll see how to do that later on. But for right now, this is illustrative of how to use the GOT, so bear with me. So that gets us message, but it doesn't get us put S. And it's not obvious how we would get to put S. Well, let's try something else. Another thing that you can do is you can use WRT ... Very simple. Notice the two periods. And if I say thing with respect to dot dot dot, this creates a link time relocation for the 32-bit difference between a slot, an 8-byte slot in the global offset table, and the global offset table. That's a little bit complicated, so suppose here's offset 0 of the global offset table. Right, global offset table plus 0. The global offset table is, think of it as an array. So the 0th entry occurs at the global offset table's address. The first entry occurs at plus 8, the next one at plus 16, and so on. One of these slots is created and reserved for the address of the thing. Okay, so this is going to hold an address that points to the thing, and that could be anything, anywhere else in the program. It could be putS. And this thing with respect to dot dot dot, that resolves to this difference right here. It tells us what is the offset into the global offset table at which I find the 8 bytes for the thing I'm looking for. All right. So when I use that, that tells the assembler, create a slot in the GOT, create a link time relocation. So if I had code up in the text section that points to this, it creates a link time relocation because the linker knows how to find this. And then add a runtime relocation for the content of that slot. So at runtime, the runtime system will know where thing is located, and it will patch that slot in the GOT. So several things happening here. What does that look like in practice? It looks like this. So we would go ahead and say move into R9, put S with respect to dot dot dot. Now, what is this giving us again? This is a link time. This is going to be replaced by our link time relocation to the slot inside the GOT. So if it's the first one, it's going to put zeros in here. If it's the next one, it's going to put 8 in here. The next one's going to put 16, and so on. And that number is going to go into R9. That's the offset into the global offset table. Well, I know the global offset table starts at RBX. So if I add RBX and R9, now I have the actual virtual memory address of the slot where those 8 bytes are located. Now, I don't want that address. I want the address held at that location, right? RBX plus R9 is the value of a pointer to the slot. I want the contents of the slot, and I get that by putting it in square brackets and calling it. This is the usual use for square brackets, right? I dereference a pointer. Again, LEA does not do that. So when I have square brackets in an LEA instruction, it's not dereferencing it. Unless confusingly, it's over here on the target. Don't even think about that. So there you go. So this then calls whatever address is stored in the GOT, and in this case, it would be the address of putS. So the linker fills in the argument or the operand for call, and then the dynamic loader fills in the slot that this is pointing to inside the GOT, and then this call works. And does it work? It actually does, in fact, assemble and work. And there you go. And we could have done the same thing up here for message. We could have created a slot in the GOT to hold the address of message, but that's kind of overkill, and it's not what's usually done. And if you wanted to do that, here are the instructions you would use to do that. Down here. All right, so now we have built an Hola Mundo dynamically linked executable. We could build this and run file on it. It would tell us it's dynamically linked. That's great. Let's see what those relocations actually look like. We can do that with readelf-r. So if we look at the object file, the .o file that was created by the assembler, we should see a bunch of stuff there. And in fact, we see something that's pointing into data. That's going to be pointing to message. Something pointing in at putS. That's going to be that relocation that will ultimately go all the way up to being resolved by the dynamic loader. And we see these have a type over here. And these types are specified by the AMD64 calling convention. Okay. So then we link, and we can look in here for relocations, and we find there are a couple. In particular, here's this putS at glibc, and sure enough, that's in the global offset table, 3FD8. How do we know that? We could look at the address for the global offset table, and we'll see it starts at 3FB as in boy 8, and runs for 48 is hex bytes. And so that runs from 3xB8 to 4000 hex, and that comfortably contains the 8 bytes that are located at this position right here. So sure enough, this dynamic relocation points to an address in the GOT. What goes there? putS. There we go. The linker has figured out that putS should be supplied by glibc. Doesn't have to be, and that can be a weakness in the system that could lead to an exploit, an actual vulnerability and exploit. And so there's some work that's done to help prevent that. But putS is provided probably by glibc. So when the linker put it together, it said, hey, you're going to need putS, but you're also going to need this glibc library. That's why when you run LDD on your program, you'll see that listing. There you go. Well, what's that? So it's worth stopping for a moment and looking at that. There is this odd looking relocation here. And what's happening here? It's at offset 1136. That's not in the GOT. So where is it? And it turns out it's in the text section. So if you look at the text section, that runs from 1040 up 195 hex bytes. So that comfortably contains this address right here. This is a relocation inside the text section. We didn't want those. We didn't want that at all. But wait. From the assembler, we had this. We had a relocation right here that was for the address of the global offset table. Oh, no. We don't know the address of the global offset table until runtime. Sure, it's a global symbol, but that means it still doesn't have an address. It has to get patched, and it can only be patched by a runtime relocation. Oh, we still have the same problem we did before. So let's stop for a minute and go again over who knows what and when. I think this will be helpful, because this can be confusing stuff. How can you figure out where your code is at runtime? That's the problem we need to solve, right? If we can get one of these virtual memory addresses, we can use all this offset stuff to get us the rest of them. How do you even do that? So here's an attempt, a little piece of code called getAddress. We push RVP, we move RSP to RVP, and then we take getAddress and we load its address into RAX, and we return. So the return value for this would be the address of this. Will this assemble? It will. Will it run? It will run. It also contains a runtime relocation, because again, I don't know this until runtime, so I can't actually put a value here until runtime. So this results in a runtime relocation in the text section, which is the whole thing I didn't want. But this works. What's happening here? Let me walk you through this. So here I call .getRip. That's right here, pointing at the first byte of this instruction. Where is the instruction pointer pointing when I call this? It's also pointing at the first byte of this instruction. So this call results in the address of the first byte of this instruction, or another way to say is the address of getRep, being pushed on the stack. Normally that address will then get popped off when I do a return. I'm never going to do a return for this. I immediately pop it off right here. So after these two instructions happen, at runtime, RAX holds the address of the label getRIP. So be sure you understand that. So at runtime now, RAX holds an actual virtual memory address of a real thing in my code. I've gotten it. That's great. I have to do that because I can't access RIP directly. I have to do it indirectly, taking advantage of a side effect of the call instruction. But it works. So now I want to turn that into the address associated with the label getAddr. How can I do that? Well, the assembler knows how many bytes there are between these two labels, right? It knows how many bytes this push takes, this move, and this call. It knows how many of those take. And so it knows the difference getRIP minus getAddr. It knows that number. So I just take this, the address of getRIP, and I subtract that difference from it. So it might look here like I need to know these two addresses. I don't, because I actually know the answer to this, to the subtraction, without knowing either one of the two values. I know that number. So the assembler will fill this in for me. I subtract that from the virtual memory address of getRIP, and I get the address of getAddr. I then return that because that's an RAX, which is my return value in the AMD64 calling convention. There you go. There are no relocations in this file at all. No link time, no runtime, none of that. That's because this is code that runs at runtime to figure out where it is. And it works. Can we use that same trick? Okay. The assembler, again, it knows offsets within a section. The linker, it knows offsets between sections, but in the same ELF file. The loader knows actual VMAs. Okay? Just reminding you of that. Keep that in your head, because you'll need that to understand some of the things as we go forward. I'll mention some special assembler labels because you'll need this knowledge as well as we go forward. We say that the token $ represents the current position in the assembly, or let's say the current VMA for it, but we don't know what that is. We've seen it used, again, to compute differences. In particular, here's message, right? This is a label whose value is the virtual memory address of this capital B. Right? This message is a label for that capital, for the address of that capital B, right? It's a pointer to this string. What is .len? So len equals $, which would be the address of the first byte following the end of the string. So the byte right after this exclamation mark. It's that address. Minus message, which is the address of B. So subtracting from this, the address of B gives us the length of the string. It gives us the string length, which is the difference between those two addresses that we don't know, but that's okay. We just want the difference. And it turns out we can know that even though we don't know either one of the addresses. There's another one of these, $, which represents the address of the start of the current section. Now again, we don't know what that address is actually going to be until runtime, but we can use that to compute offsets. Make sense? So if I took, for example, if let's say message is in the data section, data section, and I compute message minus $, that will tell me how many bytes into the message, into the text, into the data section. I get it right. How many bytes into the data section it is where message first occurs. There you go. That leads us to this. WRT got PC. That may seem like that's saying, I want to know how far the got is from the program counter. It's not actually what it's doing. This is yet another use of WRT. It computes this down here. It resolves to a link time relocation for the signed 32-bit difference of the global offset table address minus the start of the segment. Think of $$ as SS statement start. Okay. So in the picture over here, that would be negative, right? Because a low address got subtracting a higher address $$ would give me a negative offset, which is fine. Again, doesn't matter. They're signed offsets. It's okay. Math is going to work. Now, that's this difference here from the start of the global offset table to the start of the current section. So now I know this. If I knew either one of these two addresses, I could get the other one, and then I could get everything else. Understand? Right? If I knew, let's say I knew $, I could then use this offset to give me the global offset table address, and I know offsets with respect to the global offset table, and I can get everything else. Let's say I could figure this address out. Well, then I could use the offset to get $, and so on. So I just need to find one of these somehow. And we've seen a trick that let us figure out the address of something in our section, right? We saw that little piece of code earlier that figured out the address of its own routine. That's the trick we're going to use to get one of these addresses nailed down at runtime, and then we'll use offsets for everything else. Here's what that looks like. Let's walk through this pretty carefully. We don't know the addresses over on the left. Right? We won't know them until runtime, and then it's how do we get them? We do know the offsets on the right. We know them at either assembly, right? So we'll know some of these at assembly, or we know them at linking. In particular, we know this at assembly time because the assembler is laying out code in the text section. And so it knows how far, what the offset into the text section is of getrep, right? It knows that offset, so it knows this distance. The linker that's laying out got in the text section, it knows this offset. It's got a concrete number for this offset. We have a trick that lets us get this at runtime. We saw that earlier, right? I do a call and then I pop into a register. Now that register is now holding the address of get RIP. So I've got this. I subtract this number from it. That gives me $. And then I use this offset to get the address of the GOT. And really, that's what happens. So this is what that looks like. This I get with my call pop. Here's $$ minus getrep, that little thing I said we needed in here. And then here's GOT with respect to that GOT PC, which the plus looks a little backwards, but think of the GOT as being after the program. And again, if it's not, this would be a negative. So there you go. That's GOT minus $. And if you see, here's getrep, here's minus getrep, here's plus $, here's minus $. The only thing left over at the end is GOT. And so now we know the address of the global offset table, and that's how you get it. And that may seem bizarre, but that's really how it works. And it lets you get the address of it at runtime, and then everything else is offsets with respect to the GOT. What does that look like in actual code? It looks like this thing over here. And this add instruction may look bizarre to you. You may think, what is that? That's not an instruction. Well, this is stuff that gets figured out by the assembler and by the linker and then plugged in. And they know how to do it. So this gets filled in with an actual constant value that's added to RBX, which is the address of getGOT, to give us the global offset table. And you may be thinking that can't be right. Google it. Look at the NASM documentation. This is how it works. And this is how it works this is how you get these things on just about every platform, except ones where you don't have virtual memory and things moving around. Then you can use concrete addresses. But the rest of the time, you have to do tricks like this to get that information. Just the way it works. So we can go back to our Hola Mundo program, and we can use this trick in it. And so here's our Hola Mundo program, a new version, version 4. And you'll see we're now getting the global offset table using that trick. Here's our call to get got. Here's get got, and we pop RBX. We then add the offset to it, so at the end of this instruction, RBX holds the address of the global offset table. And then we do the same things we did before to get message and to get putS. There you have it. You can check it with file. We have a dynamic executable with no relocations in the text section, and that's what we ultimately wanted, and now we finally have it. Do you actually see this stuff in practice? You do. If you look at 32-bit code, you'll see these thunks everywhere to get addresses, to get known addresses. And in a single program, you might see lots of them, and they typically take this form. So this is 32-bit code, so we're going to see EAX and ESP, because in the world of 32-bit code, ESP is actually the stack pointer. That's not your stack pointer. You're in the 64-bit world. Your stack pointer is always RSP. But in 32-bit world, there it is. And so you see what happens. Someone would call x86 get PC thunk AX, and it would immediately shove that value off the stack, the value at the top of the stack, into EAX, which is the return value, and return. Why doesn't it pop that value? Well, think about that for a minute. Why wouldn't it pop that value? Why didn't it just use pop? So you should be able to figure out why I cannot use pop at this location. In fact, it kind of ought to be obvious to you. If it's not immediately obvious to you why I can't use pop, why I need to actually move this value, copy it off there without changing the stack pointer, I direct your attention to the return instruction and ask you to remember how that works. All right, enough said. And you may see many of these. This one happens to put it in EAX, but you may see other versions that put it in EDX, etc. You'll see lots of them in there. You won't see these in 64-bit code because we have a trick that the 32-bit people don't have. We'll cover that. So let's go back to dynamic linkage. So our code has no relocations in the text section and doesn't need one for the GOT, but it still has to figure out where putS is located, and that's not in our ELF file because we didn't statically link it. So we cannot know until runtime. That gets fixed by the dynamic runtime relocation. Here's our statically compiled version of it, and here is the dynamically compiled version, and there is the interpreter. Right? What is this thing right here that's mentioned? It's actually a file on your system, right? It's in lib64 LD Linux. It's there. There's a file on your system called that. It is the program loader, or the dynamic linker, or the program interpreter, whatever you want to call it. Those are all synonyms. I don't think people usually call it the program interpreter, but since the system does, we might as well include that as well. It's normally called either the program loader or the dynamic linker, or you can mix the words up into a jumble and say it's the dynamic program linker, or the program linker, or the dynamic loader, whatever you want to call it. Those are the words you need. And it's a real thing. It's just there. So if I take a look for lib64, there it is. And it runs. I can run it. And when I run it, it says usage, LDSO. It's not called LDSO. There is no link to LDSO. This is a holdover from the before times. So it's another name for this. But it's not used. And it says, here it is. You run this, you can give it options, and you give it an executable file and the arguments for your program, and it will run your program. But first it resolves all the dynamic relocations. And it tells you a little bit about it here. You can invoke it directly, and it says, mostly people don't do this. The system invokes it for you. Why are you running me? And it even goes so far as to say, chances are you did not intend to run this program. But you can. You can. And there are some neat things about it. So let's run it again. Let's use this little dash dash list, and let's pick on a program in our system, like ls. And if you've forgotten what this does, the $ in the parentheses say, run the command inside here and insert the output here in the bash shell. It's the same thing as if you've seen people use backticks. That's fine. I just, for scripting reasons, because I write a lot of bash scripts, I tend to sort of prefer that. So if I do that, this says it will list all the dependencies and how they're resolved. And I get this output. This tells me, hey, ls needs a bunch of stuff. It needs this lib se linux.so.1, and that is resolved to this specific file. It needs the standard C library, and that resolves to this specific file, and so on. It needs a dynamic loader. Well, that's the thing we're running, so we're good. It says, it tells you all this stuff. And this may look familiar to you. You may say, I've seen this kind of output before. You probably have. You probably saw it when you did this. And if you've ever done C programming and worked with dynamic executables, you've, I'm sure, done this kind of thing to see what's there. LDD, which lists the libraries and how they're resolved, gives the same output. And there's no mystery as to why that happens. LDD is actually a bash script. And this is the bash script. And what it does, you see down here, it figures out which version of Linux you're on and which one of those dynamic loaders is available, and it runs it. And see, right there in the middle, that's our friend. And it's going to run it with the dash dash list option. And I'm not finding it directly. I think it's probably uses some synonym. But that's basically what it does. It's going to go in here and run it. Fumbling around. All right, so why does any of this matter? Well, it matters because this is the program that's responsible for starting up any dynamically linked thing on the system, and everything is dynamically linked. Right? Bash, the shell we're working in, dynamically linked with that interpreter. You want to list the files? Dynamically linked with that interpreter. Everything is going to be that way. So this is a pretty important file on the system. So if we happen to look at it with file, well, this will tell us it's dynamically linked. But if we try to look at the libraries in it, it'll tell us it's statically linked. That's because this thing has to live in this sort of in-between space. It has to be aware of and understand dynamic linkage, but it also can't be dynamically linked because nobody's going to solve the dynamic linking problem for this piece of code. Its job is to solve it for everybody else. So it's kind of got some weirdness associated with it. It's a little bit special. It's loaded first. It loads any required shared libraries and maps them into your process space. It fixes up any remaining dynamic relocations, and it runs your program. So when Linux starts up your process, nothing exists, and then a process space is brought into existence, a memory map, a stack is created, etc. for you, and the operating system maps this program, because you said it was your interpreter. It looked in the ELF file, it found this program, it maps it into that space. So now that thing exists in there. And then it maps the rest of your stuff into the address space as well, and then transfers control over to this guy. So the world starts up, now there's a stack, now things are going in your process, and your start isn't called, the start for LD Linux.so is called, and it gets control. and it has to then do this resolution and then eventually start your program running. Now, it just jumps into your program. Your program isn't going to have to transfer control back to it at the end because it doesn't have anything to do at the end. Right? When your program terminates, it just terminates. There's nothing that needs to be cleaned up from this. It'll be cleaned up by everything being deallocated. There's a neat trick to this that's maybe worth considering. You can use it to run programs that aren't marked executable. I find that absolutely fascinating. So you can't run a program unless it has the execute permission bit set. You're told that, that's how it works. You got to use chmod plus X before you can run something. You can't run things that don't have the execute permission bit set, except that this can. Again, this doesn't know anything about permission bits. It just knows, hey, I'm here, I got this program, and I'm going to run it. So, for example, if I copy ls over here, just so I have it, and I chmod this, there it is. It's readable, but it's not executable. If I try to run it, it'll say permission denied, you can't run it. But on the other hand, the dynamic link, it doesn't know anything about permission bits. It says, oh, here's some code you want me to run. Here, I'll run that for you. And I can run it with arguments and so on. There you have it. So if you did something, if you got yourself into a really weird pickle and you somehow made chmod not executable so you couldn't fix, there's other ways to patch. Let's not get into that. We'll get into a wormhole here. But one way you could fix it is you could then run chmod using this and change it back to being executable. All right. So we've already talked about this. You can use it to see what's in there. I do mildly point out that this lets you specify the library search path. And if you remember, I said that where putS came from, so let's go ahead and do which.ls again. It needed to find these libraries. And so it looked on the system in a certain search path and it found them here. These things, by the way, at the end are virtual memory addresses. And because of address space layout randomization, if I run it again, they'll change. This is just where they got mapped this one time that it ran. So it finds them. Suppose I can change the order in which it finds these. Suppose I put some. Suppose I make my own standard C library, my own libc, and I have to make the whole thing. Let's say I make this part of it, and my libc, my little tiny libc, includes putS. It might find it first. If it finds it first, it finds my putS first, and it runs it instead of the one that comes from the OS. That would potentially be fun. Can that happen? So suppose someone has admin privileges, and suppose you have an alias to their shell and can make some minor changes, right? You could add an alias that says whenever they do an ls, actually what you should do is you should run this thing to run ls. It'll work just the same, but I might do something like use a switch like preload. So here's some code over here on the right. And this code, not very complicated, a little piece of C code. It defines a function called putS that takes a constant character string pointer called buffer and returns an int. Well, that's actually that's straight up the function prototype for putS in the standard C library. What does it do? It allocates a message, Salam Dunya, and it gets the length of it, and then it uses write to write that message out. And it returns the result of that, which will be the number of bytes written, which is what putS is supposed to return. That works. So let's go back over to here. Let's move this over a bit. And I think I have Yes, there's my put s. There it is. If I can type, I can make it. And now what I have is a shared object library. Right? It's not an executable. I'm not going to be running it. Some shared object files you can in fact run. This is not one of them. This is not going to how to run it. It's going to do the wrong thing, and you're going to get a save fault. Fine, fine. Don't do it that way. But what I can do is, remember the lib64 trick of saying running like Ola. Which one did I choose to run here? Ola 4. That's right. The final version that we dynamically linked. Whoops. There we go. Now let's try it. There we go. Ola Mundo, which is the same thing I would get if I just straight up ran it. But I could also tell it, you know what? Go ahead and preload a library. And that library should be myputs.so. And that'll be in the code directory. And now, instead of running the correct puts, I run my malicious puts and get a completely different output. This can be used for non-malicious reasons. Maybe I want to patch a program for debugging, or because something has changed, I need to make a change to it. I can use this kind of a trick to make that change. There you go. I've used it in the past to manipulate the output of programs so that instead of outputting just some raw text, they output formatted JSON. Because that was useful. And you can do this kind of thing. And I could even make an alias. So I could say alias ls, and then I could do something malicious with it, add that to there, and you might never know that's what's actually happening. All right. Not advising you to do any of this, just pointing it out as we go along, because again, this depends on a set of assumptions, and those assumptions are not enforced. They're just the thing we assume to be true. All right, back to dynamic linkage. Our assembled and linked program still has a location for puts in it. There's the actual address of the 8 bytes that will hold the address of puts. This specifies the symbol. This 2 is actually the index of the symbol. And you can find that out because if you look in elf.h, you'll see this #define, which tells it how to extract the symbol number from it. You see you shifted over 32 bits. 32 bits is 4 bytes. So there's 1 byte, 2 bytes, 3 bytes, 4 bytes, and then we're left over with this 2. Okay? So the first 32 bits of this specifies the symbol. It's a little truncated here. And then the last 32 bits specifies some other information. Go and look at the ELF file information if you want to know more. If we look in the symbol table with readelf-s and we look for symbol 2, right, symbol 2, symbol 2, we find out it's this. And shockingly, that's what it shows down here. That's what we're looking for. Once we have something that provides that symbol at some VMA, we will take the address of that symbol and plug it in. And sure enough, there is in fact a library, libc-so6, that starts at this virtual memory address, and there'll be an offset inside that file to the actual code for puts. I add that offset to this virtual memory address, and then I go back and patch that relocation, and now the address of the puts function is there. And there you go. I mentioned address space layout randomization, things move around. You can turn that off by using, for a single instruction, by using this. Setarch uname-m, that's the machine type, and then turning off relocation. And then you can run whatever you want to run, and it'll always load at the same address. So we could go and look inside libc6, right? We can look in its symbol table. what we'll see is here is the offset to put S. Okay, there's the offset to put S. There's the address where it loaded libc. This plus this is the virtual memory address of put S. And that's how we get it. Whew, a lot to go through. So up at the top, let's take a look at that. Here's how we dynamically link the code. So this is just assembling. And that's the and then here I call the linker, LD. My output file is this. That's just the base file name without an extension. So in this case, it'll be OLA5. And then I say I want to use a particular dynamic linker, and I specify this one. You can specify the one you want to use. If I'd written 32-bit code, I'd specify the 32-bit dynamic linker. If I wrote my own dynamic linker, I'd specify it. Lots of things you can do. I give it the object file that I want to link, makebase.o, which comes from the assembly. So that's going to be ola5.o. I say, hey, I want the C standard library to be included, -lc. You may have done this if you've ever linked a program with LD. This is all on one line. It's very verbose. There's actually a synonym for this in the make file. All right. And now, with that in place, we're going to build a dynamically linked executable. I do mention now here that the make script I give you has makeDin, which is a synonym for most of this. You still need to say -lc to specify that you want the C standard library. Okay. That was very complicated. The AMD 64 architecture made things better. You might not have to think about the GOT again, but you might have to. It's still there. It still does its stuff, and there are occasionally reasons to consider it again. A complex procedure involves lots of interactions. So there's lots of things going on. There are different components, the assembler, the linker, the loader. They are all providing a bit of the solution to the problem. And they interact with each other. Right? Each one of them passes some information along to the next and may pass some problems to be solved along to the next. And depending upon how they do that, those problems may be correctly solved or not or whatever. If I could arrange things, let's say, so that I knew the outcome of a patch that the linker was going to make to my code. Let's say I have a piece of static linkage in the code, an 8-byte offset, or a 4-byte offset. Let's just pick on 4-byte offset, and I know what that's going to be because let's say it's always the same thing, and I've checked it. And I know that I can arrange things so that I get certain bytes. And I know those bytes disassemble in a certain way. I can point a relocation anywhere in that file. And so I could write benign assembly. But I could include a specific relocation. And I can force that in there by modifying or patching the ELF file or by other tricks as well. I put a relocation there that overwrites perhaps part of the code with a link time relocation. So here's my assembly. You can look at it and go, that looks fine. I assemble it. I patch the assembly. I then link it. And the linkage causes the bytes of my instructions to be overwritten. And now I have a malicious program that you happily distribute. Right? Tons of stuff like this out there in the world. Where each of these things interact, you may have the opportunity to expose a vulnerability to the system. Let's talk about relative addressing. We want to write position-independent code. And so in addition to having a dynamically linked program, we'd also like to make a position independent one. So we add this switch -pi, which says make my program delicious. Make it position independent, meaning I could move it around to other locations because of ASLR or whatever. And so we add this switch, and sure enough, the assembler and the linker are happy with that. The assembler doesn't care. The assembler doesn't know about position independence, doesn't care about it. It just assembles. The linker does care, and it sees this -pi and it says, I will make a position independent executable. And what it basically does is check to be sure you haven't done anything that can't be position independent, and if you have, give you an error. But everything's fine in here, and so it sets the position independent bit for our file, and now the loader sees that and knows it can load it wherever. It doesn't have to be. You could take that switch off, and you'll see that it's not position independent anymore. The loader always puts it at the same location. You put that in, the bit gets flipped, and it can go anywhere. That's great. And so once we compile our Hejverden file here, we'll see that every time we run it, this thing prints out its start address, and you see that changes. So really quickly, let's walk through this file. So global start, extern printf. I'm going to call printf, which is in the C library, so I have to link with C. So I do -lc. I'm going to do the global offset table thing, so I need to declare that as extern. Here's my text section. _start. I'm not starting from the C runtime, I'm just starting up. I call getGot, here it is, I get the address. I use that trick to get the global offset table address. I get my format string with respect to an offset from the GOT. I add the GOT to that offset, load that address into RDI, which is the first argument to printf. I go ahead and get the address of start up here with respect to the GOT. I add the address of the GOT to it to get the absolute address, which I put in RSI, which is my second argument to printf. I go ahead and call printf with respect to ..got. That gets the offset of the slot inside the global offset table and puts that offset in R9. So absolute address in RDI, absolute address in RSI, offset in R9. I XOR EAX with itself, which sets RAX to 0 because of the 0 extension rule. I need to do this because I'm not passing any floating point arguments to printf. You have to think about the calling convention. The calling convention and variable length, variable argument length functions like printf interact in a funny way. And you don't necessarily see it when you're looking at these things because they just sort of work. But if you've explicitly written code that uses variable argument lists in C, you know that there's some hinky stuff you've got to do involving some specialized macros and null termination and that kind of stuff. Well, again, we don't know the order of certain things when they arrive at our code. In particular, we don't know the ordering of like floating point stuff. And unless someone tells me I have a floating point argument, I don't know that. And so the way we do that is we put the number of floating point arguments we're passing in EAX or in RAX. And in this case, there's 0, so we set it to 0. That's it. This is actually in the calling convention. Look in the calling convention, you'll see that RAX is used by the calling convention to provide the number of additional arguments for VAR types things. In this case, it's just floating point. So, again, address, offset. Well, here I turn that offset into an address. I add the offset to the slot, to the address of the GOT, and then I dereference that and get the actual address of printf and call it. And so I've passed a format string, Hejverden, with this little hex thing, and I've passed this thing as the second argument, so that's going to be plugged in here, and it prints this out over here. And then I just do my exit. All right. Position independent executable. this is really complicated, isn't it? I mean, it's just two lines instead of one, but there's addition and there's funny WRT stuff. It's kind of ugly. And one of the things that I keep saying is we know offsets. I know, the linker at least knows how far, for this first one, how far dot format is from let's say, the start of the next instruction. It knows the number of bytes between the start of this next instruction and the address of this capital H. It knows that. The assembler knows how far underscore start is from the start of this next instruction here. So couldn't we find a way to just, it would be great if we could just say, you know what, I don't know what RIP holds. I don't know the absolute address, but I know it points to the first byte here. And I know how far the first byte of this is from start. So what I'd really like is to take RIP and add it to this distance to get the absolute address. And for that matter, I'd like to take the address of RIP here and add it to this distance down to format to get this. That would be great. That would be RIP relative addressing. RIP holds a real VMA at runtime, and these offsets aren't changing, so I should be able to do that. And in fact, that's one of the things that was introduced into 64-bit x86. Not there in 32. I think there's like one or two places you can use it for like branching and stuff, but for the most part, it's not there. 64-bit world, they added a whole bunch of new cases, and we can in fact do it. We love to be able to just write that and have things work. We can try it, but it won't work, right? It'll tell us you've got a 32-bit static relocation, and you can't use that in the position-independent executable. Recompile it with -fpi. That will not help, so ignore that advice. The trick is to use RIP relative addressing. You have to be explicit about this. And again, the idea is pretty simple. At link time, the code's scanned, and these offsets are fixed up by the linker. So here's what happens. You write this, and this is NASM syntax. This is not the way it works in all the others. But you would say load effective address of RSI, and here's the address I want. I want string, but I want it relative to RIP. So you'd say relster. That generates this right here. It generates load effective address into RSI of RIP plus nothing. Well, that would be the address of the next instruction. That's not right. Well, it also writes out a relocation record, right? A link time relocation record pointing to the operand if it needs to, right? If the assembler knows what this offset is, it just goes ahead and plugs it in. If it doesn't, it leaves it for the linker to plug in. So the linker would then fill it in. Once it knows the actual offset, it can fill it in. And now, we don't need to know the VMAs. We just know that whatever RIP is right here, add this to it, and that's where I expect to find stir. This is so useful. You can just say default rel at the top of your NASM file, and it will by default convert everything over to rel. If you need the opposite, you can say absolute, but there you go. And so here's what that looks like. Right. So as this instruction executes, RIP is pointing. It contains the address 1149, and we're saying add this offset to it. It's shown here as a 4-byte Little Endian signed offset. Highest bits over here. It's 0, so this is positive. There's the value of RIP. We do the math, and it turns out this is pointing to address 4010. But it's relocatable, right? If I move this around, these numbers change, but this number doesn't, and I can always get the correct number by just adding the offset. So here we use RIP relative addressing. We just say, I want to load .format into RDI, do it with respect to RIP. I want to load start into RSI, do it with respect to RIP. And we're done. This works. Okay, great. We can look at it at objdump and see what it looks like. The problem is we can't use it for the call to printf because we don't know the offset to printf because we don't know where printf is going to end up. until runtime. So that won't solve that problem. But suppose we do this. So back here we do all this funky math to get the address of the global offset table. But again, the offset from our code to the global offset table is fixed when the linker runs. So really, I could use RIP relative addressing to get the address of the global offset table, and yes, I can in fact do that. That works. And life is much simpler, isn't it? Right? Because now RBX holds the actual virtual memory address of the global offset table, which we're getting at runtime using this trick. And this holds the absolute address of format and of start. I put it all together, and I still have to do this. Right? I still got to add the global offset table, and here's the slot that holds the address of printf. And I still got to have a dynamic relocation in the GOT to patch it, but there it is. But we can still do better. One of the problems is having to do this trick right here, these 3 lines. Well, ignore this XOR EX, these 2 lines, right? I've got to get GOT, but then I got to get the offset, and I got to add it. Can't someone else do it for me? They can, and it's called the procedure linkage table, the PLT. Here's the idea behind that. We want to use RIP relative addressing for procedure calls. The problem is we don't know the address of the procedures. But I can know the distances between things that are in my ELF file. So suppose I had the linker create a table, we'll call it the procedure linkage table, close to the code, let's say within a 32-bit signed offset, and it's populated with stuff like this. So instead of just being populated with an address, I put actual code in there. And that code is jump, and notice the rel here, I'm going to use RIP relative addressing, to the slot that's in the GOT. So this rel and this slot in here, that points to the address. I dereference it, right, the square brackets dereference it, and this says jump to the address contained in the slot in the GOT. Get the address of that slot using RIP relative addressing. Wow, that should work just fine. And then instead of calling this directly, I call this thing. So I call this does a jump, and the code runs. Okay, we'll go through this in a little more detail to be sure you get it all. So I can do this because I have RIP relative addressing. Who fills in the GOT? Dynamic linker. Who fills in the PLT? The static linker. Okay. In the 64-bit world, it's going to fill this in before start gets called, before our start gets called. Remember, the linker runs first. The dynamic linker or the program loader, it runs first. And it can go ahead and fill all of these in, all these relocations in. That's called eager binding, and it's required by a certain security feature on Linux. And if you want to know more about that, I've uploaded a video. Look for the Relro video, and it will tell you a lot about that. It's sort of an aside, so don't worry too much about it. But it might be helpful for you to know how the program gets started. And it also mentions some vulnerabilities. Vulnerabilities are fun. And so I'll skip over this. You can watch the video, and it'll go into this in much more detail. The way I make all this work in my assembly is I use another feature of NASM's WRT, wrt.plt. And so what I write is call puts with respect to the PLT. Here's what that looks like. Lots of things going on here, right? This is going to get replaced with a link time relocation, a static relocation for the 32-bit signed offset from wherever I am in the code to the instruction in the PLT. Remember, the PLT contains code. So here's my text section. Okay, the linker can fill this in because it knows the offset to this slot in the PLT. The linker can fill this in because it laid out PLT and GOT, and it knows the distance to here. So it can lay out the offset here. It knows how far this is from RIP here. So it can lay this out. It does not know the address of put S, so it creates, same as it did before, an 8-bit dynamic relocation for the address of put S in the GOT. Whew. At runtime, the dynamic linker runs. It patches this address with whatever the correct address is for put S. When I call put S, when I call it, I call actually not put S directly. I call the instruction in the PLT. So I push RIP onto the stack, and then I come here. And this says jump. And so I jump here, right? Because I jump to the address stored here indirectly, and I'm now running in put S. When this returns, it pops the address off the top of the stack, which is the address I pushed way back up here, and so control returns to here. And it looks very transparent to me. This is good. I don't have to get the address of the GOT at all. I don't have to fool with offsets at all. I just call a procedure and it goes. There you go. The linker is doing all the heavy lifting for me. And just to emphasize, there's both a link time relocation and a runtime relocation. The runtime relocation is right here. The link time relocations are here and here. Two ways this can all be resolved, and I can go over this here, but really the video does a better job of talking about eager binding versus lazy binding and when they occur on your system. And it actually walks through both of them in the debugger. So I'll skip this. Much simpler. Look at this. This is my new program. I load the format strings address into RDI. I load the address of the start into RSI. I zero out EAX because there's no floating point arguments. I call printf with respect to the PLT, and I'm done. That's it. I've written a program that I can dynamically link and make position independent. So much simpler. So I want you to note the underlying process got way more complicated. It got painfully complicated. But the interface got simpler. And again, those are the circumstances under which you often have a vulnerability. Right? I have this complex machinery. It presents a simple interface to me that hides that complexity, and that can be a problem. So let's finish up with talking a little bit about the calling convention, and we'll talk about strings and loops in assembly. Back to the AMD 64 calling convention. I've had some questions about this, so I think it's worth spending a little bit of time on it. Here is a piece of code, and it defines a little function called subfunc, and that little function takes a few arguments. It takes 1, 2, 3, 4, 5, 6, 7, 8, 9 arguments. It's quite a few. Some of them are 32-bit unsigned integers. Some of them are 64-bit unsigned integers. There's a double, another double. There's some signed 32 and signed 64-bit integers. There you go. Lots of stuff going on here. We compute the sum of the 32-bit integers, right? I1 and I3. I1 and I3. We just add those together, and we store it in a signed 32-bit integer. We compute the sum of the 64-bit integers. There we go, adding them all up. And you should notice that this says it's unsigned, this says it's signed. Is that going to actually matter in the code that's generated? Well, we'll see. We take the ratio of the floating points and we print everything out. And then we return I1 as our return result. So let's map this onto the calling convention. Right? We look up the AMD64 calling convention, and it tells me first argument goes in RDI. Next one in RSI. Next integer or pointer argument goes in RDX. Next one in RCX, then R8, then R9, and I'm done. I only have those 6 registers to hold arguments. First floating point goes in XMM0. Next one goes in XMM1. That's all there is, so I'm done. What happens to I7? Well, it's left over, and it goes on the stack. The calling convention tells me it gets put on the stack. Whew. Well, I know this holds the first, and this holds the second, and this holds the third, but I don't know how that relates to these. And so actually when your code is called, it does not know the ordering among floating point and integer or pointer stuff. It just doesn't know. That information is lost. And that's true in C as well. It's really true. So here's some code that calls our little routine, right? Here it calls subfunc, and it's got some stuff after it. And here's the function prototype for subfunc. Let's compile it. So we compile the code, and let's see how the calling convention gets implemented. And we wind up with the code you see over here on the left. This is subfunc disassembled. And over here on the right, I've kept the information about the calling convention. So I1 we said was an EDI, I2 is an RSI, I3 is an EDX, I4 is an RCX, because these are 64 or 32-bit. F1 was an XMM0, F2 was XMM1. I said I7 was on the stack? We got to figure out where that goes. So we'd like to know where that is. Maybe we'll figure it out. Here's the initial stack before we call anything. RSP is pointing to the last or the lowest byte of the last thing pushed. I push I7 because I got to pass it, right? And then I call our little function, which means RIP gets put on the stack. And I'm in our little function, and I push RBX. So where is my argument? Well, my argument is 16 bytes past that, right? 8 bytes, 16 bytes, it's right here. So I'm at that location. And this is wrong. There's an error in this slide. I'm just looking at it now. This should be plus, right? Because here is my stack address. I add 8 more. This is RSP plus 16. I don't know why I have that. RSP plus 16, RSP plus hex 10. Sorry. And here we go. Here's our code. And you can see RSP plus 16 right here. It is, in fact, plus, which is what it should be. Yeah. And so, why are we pushing RBX? Call E saved register. Why are we popping it? Because we're restoring it. Now, I've kept track of what's happening here in an interesting way, at least maybe interesting. The initial value of all of these things, I'm marking with a subscript 0. That won't change, right? Your weight at birth is whatever your weight at birth was. It doesn't change later in life, okay? It's always what it was. And each time I assign it, each time I change its value, I will increment the subscript. So EBX1 is the value that results from this assignment, and it's always going to be that value. So when I see it later on, it'll still be that same value. This way of doing things is called static single assignment, SSA. We will spend a lot of time talking about it later. It's really useful, but for right now, let's just walk through and use this to just keep track of things. So once we have all of those, I can take advantage of that. Here are the little equations I got. I just basically copied down all these little equations that I wrote right here. So every time a value changed, I bumped the subscript. And I can now do back substitution. What's RCX1? Well, RCX1 is equal to RCX0, the initial value of RCX, plus R9 sub 3. What's R9 sub 3? Well, that's R9 sub 2 plus R8 sub 0. Well, that's the initial value of R8, but what's R9 sub 2? Well, that is R9 sub 1 plus RSI sub 0. Well, that's the initial value of RSI, but what's R9 sub 1? Well, that's this. And so I do that math, and it works out to be RCX plus R9 plus the thing on the stack plus RSI plus R8. And I can map those directly back to variables in my program because of this table over here. And when I do, I get I4 plus I6 plus I7 plus I2 plus I5. And since arithmetic is commutative, I commute them around until I get the same exact statement I had in my original program. Sum of the integers. Sum of the 64-bit integers. Winds up in RCX. What happens here? Well, this is a little bit easier. And I map it back to the variables. I then put them in the right order. And this is exactly what I had in my program, sum of the 32-bit integers. Same thing, ratio of the floats. Okay, so I wind up with the results in these three registers. And now I've got this weird call to this thing called printf underscore check. What is that? Turns out that's printf. There used to be this thing called the Linux Standard Base. I guess there still is, but it's not an active project. The idea was, let's standardize Linux. Okay, so a bunch of companies came in and said, we're going to standardize this Linux. And then they got together and they created a thing called Linux Standard Base, and everybody tried to get with that, and then enthusiasm petered out, and it's had an influence, but it's not an actively ongoing thing. But one of the things that we have as a residue of this effort is check printf. And the idea is, let's check the stack when we call printf. And we'll specify the level of checking with the first argument. So what happens when you compile your code is you wind up including this thing. User include bits student standard IO ldbl.h. This gets included along the way as you resolve stuff, and this is in there. And it says inline me. And I mean always inline me. And I'm talking to you, GNU. And so this gets inlined. And what it does is it basically says, whenever I see a printf with this stuff, what I actually mean is do a printf check with this stuff. And in particular, that first argument is 2 minus 1. That's really what it says in the file, which is 1. So if you go back to our code, we can see here's the prototype for it. And we can, again, use the calling convention to map stuff over, right? The flag should be 1. That should be an EDI. The format should be an RSI. The 32-bit sum is the next argument. That's going to be found in EDX. 64-bit sum is found in RCX. The ratio is in XMM0. And the number of floating point arguments is 1, because we do in fact have 1 this time. It's in XMM0. So we set all this stuff up, and then we call check printf. And up here you can see it happening, right? So EDI got set to 1. That's right here. This says load standard out. That's wrong. It's loading the 1 that's required by the check. I must have been tired when I made the slide. Just one floating point argument, etc. So here we see all that being done. At the end, we restore we return EAX, right? That's return value, and that should be what's in here. And so we move EBX, which is EDI 0, which is I1 by the table, into EAX. That's our return, and we pop RBX and return. Whew. All right. So that's an example of what the calling convention looks like, right? You want to know what happens, right? Make yourself a little program and look at it and figure out how the compiler laid things out. Let's talk about strings and loops. So up at the top are some hard things to pronounce. Whenever you see a leading J, you should think jump. And that's what it means here. It means jump. Whenever you see a Z on the end, you should think 0. 0 flag set. If you see an NZ on the end, you think not 0. And so we see Z's on the end of these, and so you should think jump and something to do with something being 0. And it's not the 0 flag in this case. It is a register. And so in the middle here you see RCX, and that's a register. That's a count register. It's a 64-bit count register. Jump when RCX is 0. Jump when ECX, the 32-bit version, is 0. Jump when CX, the first 16 bits of that register, is 0. Those are there. They treat the count register specially. They don't test the 0 flag at all. They jump solely based on the contents of that register. So how common is this? It must be out there. Someone thought it was important to include it. I scanned all the executables in user bin on my system, and I found it in BusyBox, Blender, Pandoc, and rclone. The lesson here is the compiler doesn't like it. I think that's the lesson. Or at least GCC that was used to compile my version of Linux didn't like using these. It didn't see a time to use them. How is it used? I actually dug through BusyBox to try to figure out what was used. Looks like it's used in signaling whether to take a branch. But they're out there. I've seen them in other code. They're there. Loop instructions. Loop followed by a label. I think we've seen that before. It says decrement RCX, and if it is not 0 after decrementing, jump to that label. So here's some code, and this is the kind of code that you might see as an analyst that's there to fool you. You see less of that now that we have lots of automated tools, but you should see this kind of craziness where you're going to make some assumptions, some reasonable assumptions, because you're led to make those assumptions, and they're wrong. And so what's the exit value of the program? Well, the exit value is going to be in RDI, because we're going to do a syscall exit. So RDI holds the first argument to that syscall, which is the exit value of the program. What is that? Oh, well, that's got this conditional move. So if the 0 flag is set, the exit value is going to be within RBX. If the 0 flag is not set, the exit value is going to be whatever is in RDI at this point. So what's in RBX? Well, that's 50. Nothing else seems to change it. What's in RDI? That's 100. Nothing else seems to change it. So which is it? Well, I look up here and I see, oh, I moved to 0 right here. 0 flag is set. So the 0 flag is set. This move is going to happen. The answer is going to be 50. No, that's wrong. Move doesn't set flags. Oh, that's right. Move doesn't set flags. Okay. All right. So the flag is not set by the move. Let's go further up. Oh, this loop. This loop is going to run until RCX hits 0, at which point the 0 flag is set. That means the 0 flag is set. This conditional move happens. The result's 50. There you go. But loop doesn't set flags. Doesn't set any flags. It straight up just tests RCX. It doesn't set any flags. Okay. So I'm here. That doesn't set a flag. That doesn't set a flag. Compare. Compare sets the flags. I'm comparing RCX to 76. What's in RCX? This. That is not 76. That means the 0 flag will not be set. It will be clear, which means the return value, this move does not happen, the return value is 100. And that's in fact what it is. So, could code like this end up to, it could end up, certainly there maliciously, could it end up there because of the way the compiler does it? Yes, the compiler likes to move things into slots for its speculative execution pipeline. And this is going to take some time. And so it's probably busy trying to execute these instructions down here. And so as a result, you can often get things really far from the piece of code that sets a flag from where that flag is used. And you've got to be aware of which things set the flags and which ones don't. All right. There are some other versions of loop. There's loop E and loop Z. Those are synonyms. There's loop NE and loop NZ. Those are synonyms. There are four mnemonics, but there's actually just 2 instructions. So you can put either one of them in here, and the assembly will give you whichever one it likes. And the disassembly will show you whichever one it likes. These terminate when RCX hits 0, but they also terminate early by testing the 0 flag. And I could use them to look for something. So right here, I move 10 into RCX. Each time through the loop here, I check to see if RCX is 7. And then I do a loop while not equal back to top. So I'd go back up here and I'd keep decrementing RCX. And then eventually RCX is 7. And this causes the 0 flag to be set, right? Because RCX minus 7 is 0. So that sets the 0 flag. Not equal is no longer true. It's now equal. The loop terminates prematurely. And I put the value of RCX and RDI and move 6 and exit. What's the exit value? It might be tempting to say it's 7, but it's not. This comparison happens when RCX is 7. That comparison succeeds. I come to the loop instruction, and the first thing I do is decrement RCX. So now it's 6. And then I check the flag and exit. So the return value of this is going to be 6. Here's a different version. In this case, I compare it to minus 7. It's never going to be minus 7. So I'm going to chug happily right along until RCX is 0, and I'm going to stop. How could I tell which condition happened? How could I tell that I stopped early here and I didn't stop early down here? Well, at the end of this, RCX is not 0. But at the end of this, RCX is 0. And so what you would do to find out if you stopped early is look at the value of RCX and see if it's 0. And a way to do that is to use this jump if RCX is 0, and that's in fact what I saw in the Blender application. There you go. How common are these? They're not very common, but they're in there. I found Loopy and in a bunch of these. I didn't find any Loop Z. Why is that? It's because ObjDump doesn't produce Loop Z as an output, right? And it's not the compiler here, it's the disassembler. It emits Loop E instead of Loop Z. And I found for any version of Loop, I found 109 of these. And I looked across a few thousand ELF files. There are string instructions. The ELF has instructions that manipulate strings. This is going to get weird. Just be prepared. There are move instructions, which copy a string. Compare instructions, which compare strings. Scan, which look for things in strings. Load and store, which load from a string, load from a string, and store to a string. It may seem backwards, but if you put those prepositions in your head, it'll help. Load from a string and store to a string. And it does make some sense, right? The string is a thing in memory. And so you want to load something from that thing in memory. So it's load from a string. And you want to store to memory, so that's storing to a string. Okay. There's a whole other family of these things at the bottom that deal with the input and output ports. We're not going to deal with that much. There's the direction flag. I mentioned it before. It controls the direction for these instructions. We'll see how it works. Basically, when it's 0, you increment. When it's 1, you decrement. You can do an STD to set it to 1, which means decrement, or a CLD, which means set it to 0 to increment. This flag is commonly clear. In fact, you can probably safely assume it's clear when you start your program, right? When Linux starts you up, it's going to clear the direction flag, but it's often a good idea to clear it yourself. You won't see it very often in code because often you don't care. Why would you care about the direction in which you do things with strings? Well, most of the time you don't care, but what if those strings might overlap? Then the direction matters. So in your data structures class, you probably dealt with overlapping strings and the notion that you need to copy from one into the other for it to work correctly. Okay. How common? It's pretty common. These are pretty common. They're very, very useful. So I looked at about 1,500 ELF files. I just grabbed the stuff that was in user bin and ran it through because I was getting tired. I found 1,400 of them had this move string, and about 1300 head store, and so on. Here's what that looks like in actual code. So here's some code. It has some stuff in it. And you'll notice here's a move string, B for byte, move it in a byte-wise fashion, scan string in a byte-wise fashion, and you'll notice that there's something weird in front of it, rep and repni. These are prefixes, and there are 3 of them. And as with everything else, there are some synonyms. So there's repeat, repeat while equal, and repeat while not equal, which is really repeat while the 0 flag is set and repeat while the 0 flag is clear. There you go. How many times we repeat? That's controlled by RCX. They're prefixes, not instructions. They work the same way that the loop stuff works. And this helps avoid branching. So while this thing is spinning and doing its stuff, the speculative execution pipeline can plow right ahead. Let's see more details of what they actually do. 2 examples over here. Let's pick on the first one. So this instruction, move SB, works on bytes. There's a move SW, a move SD, and a move SQ, and those work with larger and larger chunks of memory at a single go. So if I had a string and I knew it was a multiple of 8, I could use move SQ to do it potentially faster. If I were copying a string on Windows that's encoded with UTF-16, I would know that it's all words, and I'd use move SW. On Linux, it might be a UTF-8 string, and I don't know how long that thing is. It could be any length, so I need to use move SB, as in boy, for that. B as in byte. And they use a lot of implicit registers. RSI, the source register, holds the source. RDI, the destination register, holds the destination. Shouldn't be a shock there. RCX, the count register, holds the count, the number of times I want to repeat this. Okay, so copying a string from stir to pad, this many bytes, and then this actually does the entire copy. What is stir and pad? Stir down here, you see, is this string ending with a new line. And pad is some unallocated space in the BSS section. I've done a reserve bytes equal to stir length. So I reserved a number of bytes equal to the length of this string up here in data. And this is going to just do the entire copy. So I set this up, I invoke this, copy happens. What about the second one? This says find the first exclamation mark and replace it with a period. So I'm going to use the destination register. That's the only register that I won't use the source register. I'll only use destination register for scan. Okay, only uses destination. I will put a exclamation mark into AL. What's AL again? That's the lowest 8 bits, the lowest byte of RAX. I will then put the count, the length of the string, in RCX. Now, I don't have any choice about AL. This is just what scan uses. And what scan does is it looks at the byte at RDI and it compares it to AL and it sets or clears the 0 flag. Well, that's only useful if I'm going to use the 0 flag. So what I want to do is then repeat while I'm not equal. So let's think hard about what happens. Every time through, the direction flag, which I can assume is clear, is going to tell me to increment RDI. Up here I increment both RSI and RDI and decrement RCX. Right, that's how that works. Down here I increment RDI, I decrement RCX, and I leave AL alone, and I leave RSI alone. So I come in here, RDI is pointing to the first spot in pad, AL is this, and RCX is the length. And I look at the first position in pad, and I say, is it an exclamation mark? And I just copied it, so it's going to be a W, and it's not going to be. So the 0 flag is not set. It's not equal, not 0, and so this says repeat while not 0, and RCX is not 0, so I go around again. And I do this until I hit this location right here where there's an exclamation mark. Then I do the compare. They're equal. The 0 flag is set. This repeat while not equal fails. So I terminate the loop. But this thing always does two things. It always decrements RCX, and it always increments or decrements RDI. In this case, it increments it. So RDI was pointing to the exclamation mark when I did this comparison, but then it got incremented here. And so actually, that was, after this, that was at RDI minus 1. And so I write out a byte, a period, at that location. And I have to say byte here because otherwise it's ambiguous. And then I put a 1 in there and do other stuff, and I print it out. And then I exit. And so when I run this, what I'll see is www.google.com. There you go. Whew. Only way you're going to learn assembly is to spend time reading and figuring it out, and then writing assembly programs. You have to do both. You have to go back and forth between these two to really begin to understand what's happening in this weird world of assembly. If you want to write compilers, if you want to understand what compilers are doing, if you want to hand optimize your code to work fancier, you want to analyze malware, tons of different things you can do, but it requires understanding it. And to understand it, I really want you to encourage you to play around with this stuff and see what it does. Okay, you've got all the tools to play with it. There's new homework. Homework's pretty straightforward, I think. Maybe writing an assembly language program that takes two command line arguments: a 32-bit integer, in this case it's 5, and a string, in this case it's the name Sue. And we print Sue out 5 times. Not that complicated. You'll use putS from the standard C library to write the stuff out. You'll use A to I from the standard C library to convert this thing, which comes to you as a string, into an int. On success, write out 0. If you don't get exactly 2 things, write out an error message and name your file hello.asm. There you go. There's a video uploaded called, I think, stackf.mp4. That does some explanation of what the stack looks like if you're not called from the standard C library. Well, what if you are? Well, then it follows the calling convention. So in this case, for this program, it's going to follow the calling convention, which means your first argument to your main function, argc, is going to be an RDI. Your second argument to your main function, which is argv, is going to be an RSI, right? It's going to hold the address of the start of the array of pointers to strings. So I think that's all you need to know. You should be able to do it. Send me questions when you have them. More about command line arguments. I will build your program with this line at the bottom. So your program should be buildable with this line here at the bottom. Okay? NASM to create the .o file, GCC to link with the standard library and create the whole thing. So you'll have a main and not an underscore start. Few hints. Pay attention to what is a callee saved register and what is a caller saved register. Go back to the calling convention. It's in the slides. If you want to use a callee saved register, then you have to save the old value and restore it before returning, right? Because you are the callee from the C runtime. The C runtime is the caller, and you're the callee. And so you have to save the callee saved registers that you want to use. And the common strategy is to push them early and then pop them late. Remember that leave is going to manipulate the stack. And so be sure you get the order with respect. If you're going to use leave, you got to think a little harder. If you straight up use the push and move, it'll be more obvious what's happening. if you're using caller saved registers, and every register is one or the other, you have to assume that functions like A to I and put S are going to mess them up. Because they're caller saved registers, and now you're the caller. And so it's up to you to preserve them. And the simplest thing is to push them before the call and pop them after the call. It's the easiest way to do it. All right, so you can't escape from callee and caller saved registers. You got to think about that, and you need to think about it for this exercise. Next time, we're going to talk about basic blocks and some anti-disassembly.